scale is it is never negative. Those little tiny invisible low mass particles are hitting the sides of that balloon with such a speed that it causes a force. That column of air to the top of the atmosphere would be 14.7 pounds, and that is per square inch. The first one would be temperature. Now, when you're dealing with gases, we are always going to use the Kelvin scale. Now, Kelvin scale is just the degrees in Celsius with 273 added to it. So you won't see a thermometer in Kelvin, you'll see them in Celsius. So let's say we had a temperature of 100 degrees Celsius, add 273 to that, and you'd get 373 Kelvin. If we had negative 100 Celsius, that would be 173 Kelvin. So the big deal about the Kelvin scale is it is never negative. And so Celsius can be negative, Fahrenheit negative, but Kelvin will always be positive. So in your gas law problems, always use Kelvin temperature. All right, the next thing we want to talk about is pressure, and the variable P is for pressure. Now, what causes pressure inside containers of gases? Well, it is collisions. And so let's draw some gas particles in this little container here. All right, and you learned that in the kinetic molecular theory that gas particles are always moving. And so when they collide with the walls of this container, that causes pressure. So our pressure definition is force per area. Well, the area inside my container is fixed. It is some measured amount of surface area. And the more gas particles I have in there, the more collisions I have. So that increases the force and that increases the pressure. So this is a low pressure situation. I have just a few gas particles. But what if I were to increase the number of particles? Well, that would increase the number of collisions. And so there would be more collisions per time, and that would increase the pressure inside that container. So more collisions, greater pressure. So the last little example I want to show you is inside a balloon. What keeps a balloon inflated? If anyone asks you that, you would say it is collisions, okay? Because these little gas particles aren't just sitting at the bottom of the balloon. They are constantly moving and colliding with the walls of that container, which has some stretch to it, right? And so what causes it to stay inflated is the collisions inside. Those little tiny invisible low mass particles are hitting the sides of that balloon with such a speed that it causes a force, and there you get your pressure. All right, let's continue on with pressure units. We have quite a few pressure units here, and we have atmospheres, and we have pounds per square inch, or PSI. This is kilopascals, and then we have millimeters of mercury. Why so many units? I really don't know, but let me show you how to convert units. Let's say we had 25 psi, which, by the way, that's an English unit, and we wanted to convert this to kilopascals. It's really simple. If we know this relationship between pressure units, we can convert from one to another. So I'm going to put psi on the bottom, and the unit that I want, kilopascals, on the top. Now, all I have to do is go up here to my equality, right? These are the same thing. So 14.7 psi is the same as 101 kilopascals. Well, when you multiply, the psi cancels and we're left with kilopascals, and that would be 170. So that's how you convert among pressure units. So you need to know this relationship. And there's some more. You might see a table in your book, or you can look those up. All right, let's talk about atmospheric pressure. You might see it written like this, P subscript ATM. So the atmosphere above the earth doesn't go forever and ever. All right, like it just goes to about 600 miles. So if we were to make a little 1 square inch, let's say we have a little container that is 1 inch in this direction and 1 inch in this direction, very, very small, just a little 1 square inch. And then we were to go up to the top of the atmosphere, and that's about 600 miles or so. Okay, so it's a really tall, skinny column of air. Guess how much that 1 square inch times 600 miles weighs? Well, that is 14.7 pounds. That column of air to the top of the atmosphere would be 14.7 pounds, and that is per square inch. Every square inch on the earth experiences that pressure. And I would say at sea level, right? Okay, so pounds per square inch, that is PSI. Now, as you go to higher elevations, what happens? Let's say we go up to, we have a mountain here. If we go to higher elevation, the column of air is shorter, and so atmospheric pressure is lower. So if you live in high altitude, you have lower atmospheric pressure than at sea level. All right, relationships. What is the relationship between temperature and volume? And you need to know these. Most of these are common sense. So what happens to volume as you increase temperature? It goes up. And so we say these are directly related. And then what about temperature and pressure? Think about if you heat something up at a constant volume, what happens to pressure? It goes up. And so these are directly related. Now, what about volume and pressure? Are they directly related? No, that looks like this. They are inversely related. Okay, so if you have something under pressure and you smash it, the pressure increases significantly. So lower volume, higher pressure. They move in opposite directions. Well, we take these relationships and put them all together in this glorious equation that we call the combined gas law. In the next video, we're going to work some problems relating pressure, volume, and temperature of a fixed amount of gas.